All right, so now we can calculate the reaction entropy change by using third law entropies. But how do we figure out what it is at some new temperature? All those third law entropies in the back of Atkins are listed at 298. So what if we want to find a reaction entropy at a new temperature? So in other words, what if we have the delta S of standard delta S of reaction at 298 Kelvin? How do we go to delta S at some new temperature? How do we do that? Okay. Well, we can do this just by going back to fundamentals. We know that ds is equal to dq over t as long as we construct a reversible path. Okay? So imagine what we do is we start off with our reactants. We'll just label them schematically as reactants. And let's, extra x there. Let's go ahead and take the reactants at T1. And we already know that if we take those reactants at T1 and go to products, and we could imagine doing this at 1 bar, but we're doing it at T1, right? That's going to give us just delta S for the reaction at T1. Right? So if we do products minus reactants and we look up the entropies at 298 from the back of the textbook, this is what we're going to get. What we want is to take the reactants at T2 and react them at T2. And once again, we're still going to be at 1 bar here to get the products at T2. So this is what we're looking for. So how can we get this up here by using this? Well, we can do this by making a cycle. So we can say, okay, I really want to go from this square here, I'll draw a little square here, to this other square here. And if I could do that, I could get this delta S. So what we want to do is make this path from reactants to products at the new temperature. And we can do that if we say, well, wait a minute, what if we started here and cooled everything down to T1 and then did a reaction, and then we took the products and heated them up? Well, because entropy is a state function, we know that this roundabout path is going to have the same delta S as the direct path. So, we know how to do this entropy calculation, right? We know the delta S for this step is just going to be, we're at 1 pressure, 1 bar, and so it's just going to be an integral of our heat capacities. And notice that we're integrating from T2 to T1. And we can say the same thing over here. For this delta S, we're going to be integrating a bunch of heat capacities from, in this case, from T1 to T2. If we put all those together, we can get this. When we do that, we get something that looks an awful lot like Kirchhoff's law. We get that delta S at T2 for a particular reaction is equal to delta S at T1 plus, we can combine these integrals, right? And remember that in this case we're looking at the heat capacities of the various reactants, and here we're looking at the heat capacities of the products. If we subtract this integral from that, then we'll be looking at delta Cp. And remember, if we subtract an integral, that's the same as flipping over the limits of integration. So in both cases now we're going to go from T1 to T2, and we have delta Cp, just as we had before, dt, but we're integrating delta Cp dt over T. Okay? So this allows us to adapt some delta S from some reference temperature, which is usually 298, to some new temperature. So now you can calculate the delta S for a reaction at any temperature as long as you have those original third law entropies. Okay, so just using a few hundred third law entropies that you have, and you have the heat capacities, you can then calculate delta S for literally millions of reactions at any temperature.